Доброе утро, меня зовут Volker. Я работаю в SAP, в отделе, который разрабатывает SAP JVM. Мы портировали SAP JVM на все наши платформы. Это на много CPU, как Power CPU, Titanium, Z-Architecture и на разные операционные системы HPUX, AX. Но сегодня я вам буду рассказать про Final и доклад по-английски. So, I took this picture as introduction because since I have some children now, I usually tell them some fairy tales, and often the hero dies. And but for children, it's hard to understand the concept of death, and especially in fairy tales, also then a magician comes or somebody and takes some water of life, and the hero at the end he resurrects and he's alive again, and the children are happy. And it's the same in life when then a dog or a bird dies, and the children, they don't understand it, and they tell them, well, the dog died unfortunately, and next day they ask, yes, but when will he come back? When will he get the water of life? And this is a little bit similar to final in Java, because actually according to the Java definition, a final variable may be assigned only once, and once a final variable has been assigned, it always contains the same value. That's what the Java language specification says. But in reality, it's slightly different. We will see this in this talk. So let's start with a very small and easy example. We define a final instance variable, and when we try to compile this code, the compiler will tell us that the variable f is not initialized. So, as I told before, it has to be initialized once and only once. So, if we do something like this, again, this code will not compile because we initialize it here and here a second time. So the compiler will complain that we cannot assign it 2 times. So, again, the same thing here. We have an instance initializer here, and but we have 2 initializations, one here and one here, so the compiler will complain that the variable is assigned a second time. So since Java 1.1, we can use so-called blank final fields. We can write them empty in the declaration, and later on in the constructor we can initialize them. That's perfectly fine since Java 1.1. So what about this? Does this count as 1 initialization or 2? What do you think? Will this code compile? Yeah, so this code will compile because, yeah, it's an if-else. Java-C understands this. But what about this code? It's actually the same code semantically. If f is bigger than 0, and if f is smaller or equal 0. Well, unfortunately, this code will not compile because Java-C, that's just a very restricted analysis of the code, and this code will already be rejected because Java-C thinks that f may be initialized 2 times. Also, we semantically know that cannot happen. There are other examples. For example, this code, do you think it will compile? No, it will not compile because also we know that there is no possibility that an exception happens here. Java-C does no flow analysis to detect this. And if we try to fix it like this, it won't work as well. Because Java-C complains that f is maybe already assigned at this point. Excuse me? It's the same with finally. You cannot fix it. So if we look at this code, there is no final here now, right? It's just an instance variable, and we can initialize it in the try block, and if something should happen, we give it another value in the exception block. So this is perfectly fine. Here is the bytecode of this Java-C program. So the thing is now, when we put a final here, the compiler will complain, as I showed you in the previous example. But the funny thing is, we can still write that in bytecode. So we can generate bytecode, valid bytecode, which will be executed in a virtual machine for this invalid Java code. And this is because the JVM's definition of final is slightly different from the Java definition. So the virtual machine definition only say if the field is final, a put field instruction must occur in an instance method, in an instance initialization method. That means in a constructor of the current class, and that's all. So according to the JVM definition, we can assign a final variable multiple times inside the constructor, or we cannot assign it at all, in which case it will have the default value, so 0 for the primitive types and null for object types. The same actually applies for static, for final static variables. They can be initialized multiple times in the static initializer, or not at all, but not in Java. I won't go into this. I just wanted to mention that since Java 8, it's very easy to write, to generate this bytecode here, which we cannot write in Java, because starting with Java 8, the ASM classes are part of the JDK. So you can just use them, and I just put this here for reference. If you want to try the example, you just have to use Java-C minus ignore symbol file, and then you can use the JDK, these JDK internal classes to generate bytecodes. Okay, so let's come to another problem with with final variables. When we take this example, we have a final instance variable f, and in the initializer we call a function foo, which prints f, and in the constructor we set f, and we print the value again. So what do you think what the output of this program will be? So the output will be 0 and 42. The problem is that this function foo will be called for every constructor, because it's in the instance initializer, and it will be called before the final variable has been assigned. This is valid according to Java, but it's a problem, and it's a recommendation which is in many Java books, which means don't let this reference escape from objects during construction, because in this case, this from this pointer has escaped into the foo function, and in foo, f is used as if it would have been initialized, but actually it hasn't been completely initialized. So you should never let your objects escape before they are completely initialized. So the same problem can happen with static final variables. In this example, the static initializer calls foo, and foo prints the value of f before it initializes. F is initialized with the return value of foo, and foo already uses f before it's initialized. And again, the output is 0 and then 42. This actually also happens in the JDK. There is currently a bug in JDK 9 caused by the new module system, because some of the character sets have been moved out from the runtime jar into a new image. And the problem is, if you now start Java on a Linux system, for example, with unusual encoding, the VM will not start, because during the initialization of the boot class path, the system tries to read environment variables, and for this it needs a class encoder, and for loading the class encoder, it needs to load the image files with the extended encodings, and for this again it needs the boot class path. So there's endless recursions, which leads to a stack overflow. So this has to be fixed somehow. Okay, so let's come to another. Now let's come to see how it's possible to change final values, final int values. Until now we have only looked on how we can initialize final variables, and now we will see what happens if we change them. So when we take this example, if we have public final int instance variable, and we have a set method which hasn't been specified until now. So when we create now a test e-object with 42, the final variable will be initialized. If we change it, of course, the value will be changed. So how can we implement these set functions? So there are different ways. One of the easiest is, of course, JNI, because JNI does not enforce any class, field, or method access control restrictions. Once you're in native code, you can do anything you want, and you could also change the value of final fields. So this is how the implementation of the set function would look like in native code. We just define the function as native, and then we implement it. It's just 3 lines of code. Actually, we just get the field of the field name f with the type e of the class, and then we call set int field on the object, and that's it. There is currently work underway done by Vladimir Ivanov from Oracle here in St. Petersburg to fix this hole such that optimizations can be done which rely on the finality of final fields. And he has already proposed a patch which tracks such changes through JNI calls, but it's not pushed until now. It's still working on it. This is the bug ID if you're interested. So another way to change final fields is through reflection. It's probably the easiest way. Again, it's just 3 lines of code. We get the class. From the class, we get the field. And then, of course, if we just would try to set the field, we would get a runtime error which say that we cannot change final fields. But there is this magic function here, set accessible true. So if we set the accessibility of the field, if we change it to true, then we can easily set the field. So this only works for instance fields. If we have static final fields, it's a little more complicated, because in this case, again, we try to do it the same way. We get the field f, we set accessible to true, and try to set the field. But when we run now this example program, we will get a runtime error which say cannot set static final field f to 99. That is actually what you would expect to get. But programmers are very smart, and they find a way to work around this. So it's not that hard, because once we get the field object, the field object stores the type and the modifiers, the accessibility of the field it references. And again, we can apply a reflection to the field itself, and we can get the modifiers field of the field and change that one by getting the modifiers and cleaning out the final modifier. So if we do this, we even don't have to set the set accessibility, we even don't have to call the set accessible method. We can now just set the static final field, and the value will be changed. And the problem is that once developer found out how this works, everything's possible. And I don't show you these examples because I think it's cool or it's nice, and I don't advise you to do it, but this is actually things we see in user code and in bugs which are reported, saying that our virtual machine is not working properly. And when we analyze the code, we find such things. So this one is even worse. So here, we can even, by reflection, set an int field to a string, for example, to an object of totally different type. Again, we get the field f, which is an integer field. Then we get the modifiers. We remove the final modifier, and the field object also has a type field which denotes the type. So for the integer type, the type is should be int. But we can we can change that to string, and afterwards we can change the value of an int field to be a string. So what will be the output if you run this program? What do you think? Will it work? Will it crash? What will happen? So actually everything can happen. You have no guarantee if you do such things. So here you just get a negative integer, but for example, there is a bug which was related to such changes because this is a bug in the C2 compiler, and this bug is actually related to concurrent class loading, which means if the JIT starts the compiler method, and while he compiles the method, new classes are loaded, some of the type information the C2 compiler has gathered can change. And there was a bug which led to crashes. So this bug was fixed, so it handles now concurrent class loading correctly, but the same error can happen if you do such changes with reflection, and it's not easy to fix that. Actually, I think it's impossible. But you could also get something like this. So if I run this example, I run this with Java 8. If I run it with Java 9, with the new development version, we will get just a crash. And it says, we see this was a debug version, so the problem is that it's actually not a problem. Java 9 runs with G1 by default, and G1 has some pre-barriers, and when we pretend to store an object value in a field, it updates this object values, these barriers, and then it sees this integer which was there before we stored a new string. It's not an object, so it complains. So please don't do such things. Well, another way which is possible since Java 7 is to use method handles to change final fields. It works in a similar way like reflection. First we get a field, and then we can get from the method handles a method handled setter, and by invoking the setter we can change the values of this field. And finally, the last possibility to change a final field is, of course, the beloved unsafe class, where I have been many talks about here and in other conferences and on the mailing lists. So again, with unsafe, it's a little similar to JNI. Once you get a handle to unsafe, you can actually change anything you want, and it works similar to the reflection example. You get a reference to the field, and then with unsafe you can get the offset of the field inside the class, and then you can call unsafe put int and change the field. Yes, actually yes. Unsafe it's a private class, so inside the JDK, so that's why we have to construct it again by using reflection. So it's a good reason that unsafe was put in it has private access in the JDK, because it was supposed to be used only internally by the JDK, but again, smart people found out that it's possible to use it, so you can construct it, for example, this way with reflection by getting a handle to the constructor and then use it. But it may be that it will be removed in Java 9, or maybe parts of it will be removed in Java 9, and probably in Java 10 at least shouldn't be there anymore. So be aware, not use it too often. Actually, reflection and the reflection method and the method handles I showed you before, they all go down to using unsafe. So internally, if you are using reflections, we will internally end up in using unsafe as well, because the reflection classes are actually constructing a reflection accessor for the field, and this one is using unsafe for setting the field internally. Okay, now let's come to another funny problem which has partially been shown yesterday by Alexei in his talk. So when we have something like this, we have a class which has a private final field f, which is initialized to 42, and again, we have our set method here. We construct a new object of the type test m, and we print out if the field is 42, we print out unchanged. If this value has changed, we print change. And then we print the value of f, but we get it with reflection just because it's more fun. And then we set the field to 99, and again, the same line. If the field has changed, we print changed, and then we print the value of the field. So what do you think, what two lines will be printed now? Unchanged, 2 times, 1 time, 2 times, yeah, okay. You will get a chip from me. So why does it print 2 times unchanged? Because this primitive final fields are treated as constants in Java, and they are just replaced already by Java-C in the bytecode. So the bytecode generated for this main method, it looks like this. We push 42 on the stack, we push 42 on the stack, and then we compare it. So no difference whether we are changing the field itself. The Java bytecode already compares 42 with 42 here. So actually, when we change the field and access it, we will get the correct values here. But here, the Java-C compiler has already replaced the field access by the value itself. So that's actually was not only for fun that I used reflection here, but also to have a good example. Because when I had used here test MF, we would also get here 42. So this is actually nearly the same example. We only not initialize f here in the declaration, but in the constructor. So in this example, Java-C won't treat f as a constant, and we will get the expected behavior here, changed and unchanged. And when we look at the bytecode, we see that now Java-C has first loads our test M object, and then gets the I field, pushes 42, and compares these two values. So this is actually what many people would have expected it would happen. And why is this here? Here are the references from the Java language specification. So a variable of primitive type or type string that is final and initialized with a compile time constant expression is a constant variable. And reference to fields that are constant variables are resolved in compile time, and no references to such fields should be present in the code. So this is exactly what's happened. This was also the content of a Java Puzzler 93 by Joshua Bloch and Neil Gafter, and you can find a lot of blogs and about it. So I'm now coming to a final example, which is a little bigger. So let's look briefly at this Java code and try to understand it in a few minutes, and then we will see what the output is. So we have a test class here, and this test class has a static final test field, so it's a singleton actually. And it's an object test initialized with 42. And the test class also has a final instance field f, and this instance field f is initialized in the constructor. So actually, we have a single test object here stored in a static final field with the value 42. And we have a getF function which is static. And this static getF function queries the static test field, and from this test field the instance field f, and compares it to 42. If it's 42, it just returns 42, else it returns the new value. So did you understand this example, or are there any questions? So we have a test class which has a static final field of a test object, test instance, and every test instance has a instance field of type int. So when we start now and call test get f, I think everybody agrees that the output will be 42. Now we call the set test method, which changes the static final test field to a new test object, which is initialized with 99. So I think also everybody will agree that the output of this is 99. Now again we create a new test object, and this will be initialized with 42 again. We set the new test object, we reset the static test field to point to this new object, and we call 20,000 times in a loop the getF function. So you probably guessed that we do this to warm up the JIT compiler and JIT compile the getF method. So what do you think? Will we print exclamation marks here or 42? No, we will just print 42 because, I mean, actually, we just set the field to 42 now, and now the JIT compiler compiles this, but all the JIT compiler knows until now is that the static test field is pointing to a test object which has the value of 42. Okay, now we have JIT compiled this method, getF, and now again we call set test again to reset the static test field, and we set it to a new test object which has the value 99. So the question is now, what will the getF function print now? Yes? Yeah, okay, you can take your chip later on. We print 42 because we have actually reset the static test field here, but the just-in-time compiler, and we will look at the generated code in a minute, has already optimized this field here, and because it's final, it has assumed that it will never change, and it has replaced the load of this static final field by the object itself, and the object has the value of 42. That's why we still see 42 here. Also, actually in the heap, the object was changed to point to a new static instance variable. Okay, so now we think, okay, but we still want to set it, so we still want to change the value, so we can actually access the test in the test field in the heap and call setF on and reset the integer in the static final test instance. So what will be the output here on the next one, 42 or 99? Okay, it's still 42 because we have actually changed the value of this test object here, because we called here test set test. So we changed the static final field to point to this new object, and this already has the value 99 anyway. So now we access this field and set it to 99, which has no impact because, as I told you before, the JIT compiled code is still using this for object 42. And now the last question. Now we know that the JIT has actually optimized the field access for this field here and uses it directly. So when we now change the value of this test object, test42, to have a value of 99, what will be the output here? Okay, so the answer is it depends. So it depends how the JIT compiler is optimizing this code. So let's look at this. So let's call Java test. Sorry. Okay, so actually the output is different from what we saw before. Does anybody know why? It only prints 99 now. So one common mistake if you do such small examples is that you forgot to say minus x batch. So this means the JIT compiler is compiling our method, but it's too slow. Our program finishes before the compilation finishes. So by using the x batch option, we say that we want synchronous compilation. So it means when the virtual machine decides to compile a method, it will wait until this method is compiled before it proceeds. So now we run like this. We see that when we go back to our example, we have 42, 99, 42, 42, 42, and for the last question mark, in this case, we see 99. But we could also use a clever option which says, it's hard to see, I read it for you, minus XX plus trust final non-static fields. So if you say the JIT compiler to trust final non-static fields and run the program again, you see the output will be 42. So let's have a look at the code which has been actually created. We use for this the compile command option, and we say we want to print the test get f method, and if you look at the code which was generated for the usual case, so without trust final non-static fields, we see that the JIT compiler loads here, it say test exact, so it means this is actually an object. We don't load the static field from the class, but actually we load the direct class. So because static final fields are optimized by default by the JIT compiler because he assumes their value will never change. But non-static, that means instance final fields, are by default not optimized. So we just load the static final class directly, and then from the static final object we load the integer field and we compare it with 42. If we say the JIT compiler that we are confident that it should trust final non-static instance fields, we will see that the generated code will look totally different. One second. So actually the just-in-time compiler now optimizes pretty everything because it assumes the final static field is constant. It assumes that the instance field of the object is constant, so the getF method only returns 42. That's why it has no effect if you reset the field in the heap, because it's not even accessed by the method anymore. Okay, so what can we do to prevent all these problems? So one way is to remove unsafe. We could also track final changes in SUJNI. We could also restrict access to finals in reflection. So what I forgot to mention, all these tricks with reflection, they are only always unsafe. They are only possible if you are not running with a security manager. If you're running, for example, with a security manager, then it is not possible to reflectively change these fields. But many people are running without security manager anyway. So, but the JDK itself still has a lot of places which are worth optimizing, where it's worth optimizing final instance fields. And for this, they came up with different solutions because it's so hard to just trust final instance fields, and we cannot enable them by default because, as we saw, a lot of people are using such tricks and a lot of code will break. So one thing they started was the stable annotation, which they introduced for invoke dynamic, because in the Java-lang invoke package there are a lot of places where they had final instance variables which are initialized only once when the bootstrap method is, for example, is called, and after that they never change. But the JIT compiler couldn't compile these fields, so they introduced the stable annotation, but this is only available in the Java-lang invoke package. And the hotspot source code, if you look at the JIT compiler and at the code which is generated with field access, it checks for the stable annotation, and if yes, it will treat fields which are annotated as stable, even if they are not final, as being final, and optimizes them. It's this option which enables optimization as stable fields like, in the same way like final static fields. There is also this option, use implicit stable values, which enables optimization of fields inside of the JDK, even if they are not annotated with stable. So, for example, the character field in a string class can be handled, can be seen as stable because it's initialized only in the constructor and cannot be changed anymore. Here are some bugs and some enhancement requests which handle this topic. The problem with stable annotation, as mentioned by Alexei yesterday, is that this is actually, it only works for fields which change their value at most once. And for detecting this, the JIT compiler checks that fields don't have their initial value. That means they are not 0 or null for objects. The problem is if 0 or null is a valid value of your field and you initialize it with this value, the JIT won't be able to optimize it because it thinks it hasn't been initialized until now, and so it still accesses this field. So these optimizations don't always help. You have to think about about something else. So actually, that's all I wanted to tell you about final. If you have any questions, I'll be happy to answer them now. The question was if there's something special about multi-threaded stuff. No, I think that's orthogonal to final. So, I mean, of course, I mean, if multiple threads change the field, you can also make them volatile, but volatile final variables actually make no sense because final means that you cannot change them, and volatile means you can change them anytime. So.
Thank you for your talk. I'd like to ask you the question which rises over and over again in our code reviews. Is there a point of using final keyword for parameters for every function? if we choose not to modify the parameters?
I think currently not, because by default the JIT is running without trust final instance field. So if you just have final locals in your method, the JIT compiler will detect it anyway that they are assigned only once, and will optimize that in the method. So I mean it makes sense. It makes sense for documentation purpose. So it's still good to declare them as final, because if you have a small method, it's clear, you see it in one screen that nobody changes this. But if your method is like multiple screens long, maybe that somebody who edits the code thinks that it's a good idea, now I will use this parameter and change its value and use it later on with another value. And if you want to prohibit that, you just, for documentation purpose, declare it as final, and then this will be not possible. And people would have to use a temporary variable and the code would be more clear.
Well, my question is related to the example you showed when you passed Xbatch flag to Java. Will the things change? I mean, the behavior if you pass, for example, xcomp flag. This means, as far as I remember, as far as I know, this means that Java should compile the code the most effectively.
You mean if I pass xcomp to the command line?
Yep.
I mean, it may change the example in the sense that we may have printed 42 before already, but it won't change anything in the problem. It only changes the time when the getF method would have been compiled. So it would have been compiled more early, and then it would have used the previous value of the static field. But again, if you change it after it has compiled, the compiled code will contain the old value. So you will have the same problem.
Okay, so it doesn't matter which level of compilation is used?
It doesn't matter, yeah, right. If at the time at which the compiler compiles the method, actually the compiler will use the actual value at the time it compiles the method. And if you change the value afterwards, your compiled code will be wrong. It will show the previous value.
Okay, and another question. When you played with reflection, one of the examples was about setting modifiers variable of the field, and you changed the modifiers the way that the variable, not the variable, but the field was no longer final. So does it affect the safe publication for the whole object? Because we know that Java provides some guarantees that is related to final fields about the safe publication.
Yes, so sure, this will impact the integrity of your program if you do something like this. So as I showed in this example, you could even change the type of the object, but this completely breaks the integrity of the VM. So you will have no guarantee afterwards.
Okay, thank you.
Hello, thank you for your talk. I have a question about these tricks. Is it safe to give users of JVM such powerful tool to change final fields, modifiers, or should it be strictly used inside internal parts of JVM and not by users?
Yeah, so actually this wasn't given directly to the users. The user just found out how they can do it anyway. So these means were actually for first they were introduced for the JDK itself to implement things like deserialization, where you have to change where you have to initialize an object which you deserialize. You have to initialize its final fields after the object has been created, and then they just escaped from the JDK, and people found out ways how to use them. And I mean, for unsafe, there are actually valid use cases for people who do off-heap memory or things like that. You probably know that. And but like a weapon, you can use it to protect yourself or to shoot other people. So it's or shoot yourself. And most of the people who are using these possibilities, they just shoot themselves, so without knowing it.
Thank you for the talk. And I wanted to ask, is it really commonly used in your everyday practice, or you're trying to avoid these things like changing final fields, trying to avoid it if it is possible?
I'm actually not programming very much in Java, so for me it's no problem to avoid it.
Okay.
Hello, my question is, will variable handles introduce another option for setting final fields, and if they does, should we care about it?
Yes, I think the var handles project wants to offer a way for safe access to memory and maybe also to final fields. But you have to look at the JEP, and it's still under discussion. And it's supposed to replace unsafe at some time, but it's not clear if it will give you all the possibilities of unsafe or just some of them. So there's still a big discussion on the OpenJDK mailing list. So you're welcome to join.
Thanks, Volker. Do you know of any ahead-of-time tools, well, not necessarily ahead of time, but more feasible to do it there, to detect this kind of patterns that is seen on the screen, so that some sort of analysis tool which issue a warning that you're doing something that may execute not the way.
You mean static analysis tools which detect such kind of access?
Yeah, there are any analysis tools that you know of?
I'm not sure. I'm not familiar with this kind of tools, but it may be that, I suppose that any good static analysis tool should give you a warning when you're using unsafe. So.
And what about final class? Could we use a reflection to extend final class? Thanks.
Actually, I don't know. I haven't tried it, but I don't think so, because I think this is enforced in the virtual machine. But so I don't think, but maybe, I don't know. You have to try. I mean, with reflection, you cannot generate classes. You can just, by reflection, you just change existing objects which are there already. So, but maybe with maybe you can generate bytecode yourself. But I think this should be catched by the verifier. So actually, I think it shouldn't be possible. If you run without verifier, maybe it's possible to switch off the verifier. But again, I think you shouldn't do that. So if you switch off the verifier, you can again compromise the VM in all kind of situations, so there is no guarantee anymore.
Did I understand correctly that final static equals something is the only way to get some performance boost from final at all? Yes.
So currently only static final fields are optimized by the virtual machine, right?
Thanks.
Well, as far as I'm concerned, Java uses different tricks with final for serialization, deserialization, and what can be motivation for a developer to play with final fields behavior? I mean,
you mean what become the motivation for others to play with final fields?
The code looks great, and everybody, I think, really
actually, I have no idea. I just see it in user code. I mean, sometimes users get a library and maybe they don't have access to the source code and they can change it, but then they find out by reflection that there are some fields there, and then by reflection they can change it. So it's just, most of all, it's a hack, I think. People want to get something done and they don't have the right tools to do it. And then they came up with such workarounds or hacks, and it seems to work for them. But again, there are so many, the problem can arise at so many different points. So it may be that they run just interpreted, for example, then everything works fine. But as maybe just the method get never compiled. And once it gets compiled, you only see the problem then. So if they apply such tricks and it works, it doesn't mean that it will work with every VM, it will always work. So that's just a hack. So I wouldn't do that. But sometimes I think programmers they don't find another solution, so they do it like that. They just look at Stack Overflow, how can I change a final variable, and they find this code and then they use it.
Okay, so you are not familiar with some tools probably that take advantage of these methods, of these tricks to do something useful. I'm not sure what it can be, but...
Well, as I told, the JDK is using it in a useful way. For example, for deserialization, or for example, for method handles or stuff like that. But the JDK actually knows what it does, because it's written by the same people who wrote the VM. And sometimes they need to overcome, they need to do things which are not allowed by the Java language itself, because they are actually building the Java language itself. So you cannot implement everything, every Java feature in Java itself. That's why you need to have a breakout from it. But it's not intended for general use.
Okay, so if I see the usage of such tricks in some project, should I think that, well, it is a bad project, something like an index of bad design, and so on and so forth?
Yes, I think, yeah, 99% it's like that, yes.
Unless it is JDK.
Yes. Or I mean, as I told you, unless you build your own sophisticated library for example, for off-heap object storage or things like that, which aren't easily implementable in Java. But if it's just, I don't know, a business application in your application server, then it's definitely bad to use it. You should prohibit it, yes.
Well, most of Oracle guys used to say that do not ever use unsafe, because we may remove it in next version of Java. But nevertheless, a lot of projects rely on unsafe. I think that it's just a matter of how this method is spread in the community. If community thinks that it's worth using, then it might be used.
Yeah.
Okay. It was just a thought.
You briefly mentioned the stable annotation. I have a question. Is we forced to use stable annotation on every our final field if we know it do not change? Because it looks like a horrible workaround, and I need to understand this.
But you cannot use the stable annotation because it's private inside Java lang invoke dynamic.
Oh. Is there any way I can extract it from JDK and use it in my code?
I have not tried to place an annotation by reflection. Maybe it's possible, but I think there, if I remember right, there is also a check inside the hotspot which checks that the class is inside Java lang and Java lang invoke dynamic. So I'm not sure if it works if you place. If you would succeed to place the stable annotation. Yeah, so it wouldn't help probably.
Oh, okay, you have discussed the final fields. And what about final methods? There are a lot of discussions about whether it's useful to put final annotation, final keyword for the methods, and whether it can boost performance. There are some books which say that it is good to make methods final because runtime can optimize or inline the code because the method would never be overridden in the.
Yeah, I think it's the same like with annotating parameters with final. I think it's good for documenting your intention that nobody should overload this method, but if the method is actually final in reality and there is only one instance of it, the JIT will detect that and optimize it right away and still inline it. So from a performance point of view, I think it's not necessary, but again, from a documentation point of view, it's still useful for documenting your intentions. So the JIT can even inline polymorphic methods or virtual methods. If there are, for example, if there are two implementations, it can inline both versions of them and just do a check to see what object you actually are using in the JIT code. So it can do a lot of sophisticated things. If it gets too complicated, it will de-optimize the code, sure, but I think if you have two versions, it does it. If you have more than one, it will not do it anymore.
Hi, it was a great talk. So, Java memory model offers some guarantees connected with final fields of object. How does it clashes with the possibility to set the final field in this way?
So, yes, for example, if you have a final field, a final instance field, and you initialize in a constructor, the memory model guarantees you that every thread which sees the new object will see the proper initialized final field. But again, as final fields are not volatile and you change them afterwards, you won't have any guarantee that other threads will see the change. So if you change a final field and you want to make sure the change is visible from all other threads, you would have to synchronize yourself or to use your own means of synchronization. The VM doesn't help you in this context because you're not supposed to do it. So
maybe a last question.
Okay, so thank you a lot.